to the meeting because y'all were not logged in as Cs. So do you know who y'all are? I forgot. I admitted 2 people in. Okay. So let's get started, and you can relog back in if you get logged out. So welcome everyone. This is the final project presentations for the Formula 110th racing autonomous racing course, and we're going to have 5 presentations today, starting with team 1, who are going to describe their racing approach in terms of their planning and control and racing strategy. And all teams have had to race in an online bot racing league, and we're going to see how they navigated their solution to be the fastest racer. So let's start with team 1. And so team 1, you can introduce yourselves and then share the screen and walk through your presentation. Each team gets 15 minutes to present your approach, and we'll have 5 minutes of Q&A. So let's get started.
Hi everyone, we are team 1. My name is Ding Ding, and my teammates are Shivangi Misra and Wei Tang. So let's start it for now. Give me a second. Can you guys see my screen?
Yeah.
Yeah. Can you guys see the slides?
Yes.
Yeah. Okay. So let's get started. Yeah. Hi. So in this project, we mainly do 3 things. That first we do the Raceline optimization, and we implemented the minimum curvature and the minimum time. And finally, we'll choose the minimum time. And we use pure pursuit to as the controller to track the path that we have already generated. And for the obstacle avoidance, we implemented the obstacle-dependent Gaussian potential fields. And we also do some improvements to our RRT star that we used before. And we make a comparison between these 2 methods and make some interesting videos. Yeah. So for the Raceline optimization, although we do the minimum curvature, but we think that it doesn't work well, and actually we test it and it's not fast enough, so we just give up. And besides, we use CMAES, that's the covariance matrix adaptation evolution strategy to generate a trajectory. So for now, we need to get a velocity profile that is a series of velocity to each point. What we need to do is we do this in order to find the maximum permissible velocity for the vehicle that when it's given the 0 longitudinal force. So how to do this? First, we already have a rough path, so we divide this path into several curvature segments, and then we find curvature for each of the segment. So for now, we need to compute the maximum, that is the available velocity for us. As you can see from the expression here, the mu represents the tire road friction, and the g is the gravity. K is the curvature at a point or on a segment path, and the ux is actually the maximum available speed. So, as you know that our car and any car has a limitation for the maximum force, which means that you cannot have a pretty good, you cannot have a pretty large acceleration or deceleration. So these two expressions are used to kind of constrain your velocity change. Let's see the parameter here that is called the fx axle max. That's actually the maximum available longitudinal force for acceleration, and the fx decel max for the maximum force for deceleration. So let's jump to next slides to have a clearer view. Let's first see the left part. The first plot is the curvature plot, and the second one is the maximum velocity before we make any changes. And as you can see here, that it will change a lot in a short time range. So in order to make the curve smoother and more stable, like during the acceleration, we want it to change not too much, and during the deceleration, we want it kind of have a more stable change. The plot right side is actually our testing results. We already have a 10,000 points on our path. So the blue line is actually the raw velocity that we get before. The red one is actually the velocity we want after we apply the smoother change. So as you can see that in this range, the velocity change much. This means that the car is running in a straightforward direction, so it doesn't turn too much. So next, Shvangi and Wei will discuss our methods in detail and our testing results.
So for the Raceline optimization, since we decided to go with the minimum time trajectory, we first got the center line from our reactive methods. We found the velocity profile using the method that Ding Ding just described. We divided the curve into segments, and we parameterized these curves according to a parameter alpha that shows the change in the waypoints along the normal. So if you look at the image, you can see that the blue points are the original points and the orange points are shifted versions of those points, and they're shifted along the normal. So we had an alpha for points described in different curve segments, and we used that in our optimization. They were initialized at 0. And then, can we go to the next slide?
Yeah, sure.
Yeah, we use CMAS as described in our lecture. We used a fitness function that took the velocity profile. So we also recomputed velocity profile in every iteration and used that to calculate time. And based on which has the minimum time, we spawned a new generation. And basically, that's how the iterations went. We were able to improve our lap time by 5 seconds. You can see from the image the new and old trajectory. Okay, it's fine. Thank you. The next, obstacle. So switching to the obstacle avoidance part of our problem, we were very curious about the obstacle dependent Gaussian potential fields. Because it seemed that we could use it and we could create different kinds of bumps around our obstacles, and that would kind of help us predict as well as avoid these obstacles. So the method basically takes, so from the image you can see that there are lots of laser scans, and the obstacles are represented as dips in the laser scan data. So we define a distance threshold. We find any obstacles from our laser scan data within that threshold. We find the variance, meaning the width of the obstacle, and then we compute a repulsive force that way. The next slide. we also have the attractive force, which we get from our point on our race line, our race trajectory, which exudes like a attractive force towards it. We add up all of these forces and we look for a minima in our data, and we set it as the steering angle for our car. So this was a brief description of the Gaussian fields. RRT is something that we've implemented. Some modifications we made in our version were we put in an angular constraint so that when we're constructing branches, it's always towards the the front part of the vehicle, so that we don't have the vehicle drift too much. We also see that when the opponent car is close to us, we would like to sample a little away from our goal location. Um, and so that, say we're very close and we want to avoid it, we don't necessarily follow the path that leads us to the goal through the opponent car. Otherwise, we keep the sampling close to the goal because with the smaller sampling range, we can find our trajectories faster, and that makes the car move more smoothly. We also tried bidirectional RRT star because we found that sampling time was a factor here, and it did influence our performance. So, but we saw that it did not make too much of a difference, so we didn't put it into our final code. We also had safety braking enabled. So Wei can now talk about how we compared like the Gaussian field method versus RRT star and what our final decision was.
Yes, thanks, Shivangi and Didin. I guess there's a question. So there's two questions, I guess. So
I can handle them. You can go on talking. I'll
so we ask now or like after the presentation? So
I can answer right now.
Go ahead.
Okay. Okay, cool. So actually here comes, once we want to implement the potential field method. So once we have this local planner, obviously we want to make a comparison with RT star, which we have. So actually we set 3 different tests. So can you go to next slide? Yeah. Actually, the first test is kind of like our third risk. It's we want to say their ability of avoiding obstacle, and actually we set 2 different level map, a easy one and a hard one, and we let the car run in different speed, 1.5, 3, and 4.5, and to see their performance. The second one is like there's totally no obstacle at all, and we want to see how fast this algorithm can run. So the third one is like we want to know how robust our algorithms are. So we just add some random noise to the laser scan and to see their performance. So we can jump to the potential field method performance. So actually, it's quite, when we use the easy map, it's quite good. Like it can pass all the speed level. But when we switch to the hard one, go back a little bit. Yeah. So when we switch to the hard one, like when we increase speed, actually it will go a little crazy. It will vibrate a lot, not very stable, and it will hit the obstacle sometimes. And for the test 2, actually it's quite good. It can run 11 seconds for 2 laps, so it's cool, perfect. And for the test 3, actually, it will add noise. Actually, it will, this method is more sensitive to the obstacle, so it will vibrate a lot and go crazy sometimes. So here's another 2 videos for our, the first one, as you can see, is quite interesting field case. Like it will find something like local minimum. You can see it go to a circle, and then again, there's more interesting thing. It will like, okay, I want to avoid all of them, but seems I can't find a really good waypoint to track. So it will like run a circle, something like local minimum. So the third video is show when the speed is 1.5, how good the, not good, but it can avoid the easy obstacle here. So it will vibrate, but at least it can avoid that. So let's come back to our RRT star performance. Actually, RRT star is better, but actually it can run 12 seconds for 2 laps, so it's almost the same. So the second and the more important thing is that it can pass all the case even we add noise to it. So here's some video for our RT star later. Yeah, the first one is the speed. The speed is 4.5, and it can avoid all these 3 obstacles. And the second one is, as you can see, we add some random noise to the laser scan, and you can see there's some gap between the real obstacle and the obstacle showing our occupancy grid. So as you can see, it can still like avoid this obstacle, so it's kind of good. So our conclusion is that the potential field method, when we implement that, it's kind of sensitive to the obstacle. Like if we set the threshold of the distance to be 2 meters, it will like if the obstacle is 2 meters away, it will like perform some behavior, try to avoid that. So and it also like vibrate a lot because it's like not very stable. And actually we write some stable algorithm on that, and it still will vibrate a lot. So actually our RT will give us a better performance, and we finally choose RT star and to tune them to like further use. So yeah, that's our presentation. So thank you very much.
So I have a question.
So I suggest we have some Q&A now, but let's also go through the questions that you all answered on the chat so we can at least discuss them. And but let's start with Matt's question here.
So did you consider at all combining the 2 methods? And I'll let you answer that first, then make a comment. Okay, maybe too broad. So RT is going to sample directions or sort of goal points randomly. Did you think about using the potential fields because they're distributions? You'd have to renormalize as the thing to sample from. I'm wondering if anybody tried that.
Yeah, we didn't try that, but we did have a varying sampling policy, but that was only dependent on how close the opponent car is to us or an obstacle.
Do you have any thoughts about how you could reduce this local minima problem in the future? I mean, it was sort of, most of the potential fields literature does discuss this as being a big issue. So given that you chose it, you would seem that you had some direction there.
We wanted to try reducing. We wanted to try it. We thought we could tune the parameters. We could add some interesting, like we could have like different morphologies of the obstacle field for the repulsive fields, but it didn't help. And so we switched to RRT star because we also wanted to.
Yeah. So what happened is actually this method will directly find the best point according to the data we have. So when we just implement that, the car will much more unstable, like vibrate a lot. So we write some stable algorithm, like we set a threshold. If inside that range, if that point range is small enough, we will choose that. Then we will choose that one that closest to the goal point. So when we write this one, which will make the car more stable, but at the same time, maybe it will find the local minimum, not the global minimum. So here's the kind of a trade-off. Like if we use just the best point, it will vibrate a lot, and we write this in, it will find some local minimum things like that.
Yeah, and besides, during tests we find that the potential field method seems like it performs bad when you are facing the kind of small obstacles. When you have a large obstacle, it works great, but for the small one, it works bad. So maybe what do you mean? You mean maybe we can combine these two algorithms? So I guess one approach is to define if the obstacle size is great enough, if it is really great, and you can use the potential field. Otherwise, you may use just the RT star.
Yeah, that's sort of what I meant. What I meant is use the dense. So for the potential fields, right, you have all these Gaussian bumps in the space wherever there's an obstacle. Say that it's probability 1 to sample any goal pose, or equal probability, uniform, right? And then subtract off the probability from the mass associated with the obstacle, so that you're more likely to sample in the regions that are unoccupied. Like you could have used it to inform the RT sampling procedure. And the other thing is, I guess, I'm sort of hopeful, maybe not this semester, but in the future, maybe we could communicate it better. CMAS is a very general black box algorithm. If you had problems with parameters, you can put those parameters in the CMAS search, right? All it needs is a simulation and a score. So I hope that maybe that point came across in the lecture, that it's more than just for Raceline optimization. You can use it as a general reinforcement learning method. I'm going to stop monopolizing the questions because I know there's a ton of other ones. So defining the score would not be difficult. It's just your lap time. You set the parameters for the potential field controller, you run a lap, you get a score back, you update. And this would be in the simulator. So let me go through here. So some other questions are: did you try both of these methods with the other car moving? And does it change anything?
So we didn't. So we assume that the opponent car is going to continue to move in the direction and velocity it has for a little more while, and we use that to try and evolve the Gaussian field around it in that direction. So we'd have like a oval kind of Gaussian bump, and we hope that our car would be able to avoid it. But then we had a lot of issues with local minimas, handling local minimas, and having it converge at the speed that it runs.
Mm-hmm. But so it looks like you have both methods, and maybe you're probably deploying RT star for the race. Should we expect clean races between your car and other opponents? Like, does it successfully avoid hitting the other car?
It does, except if it's sandwiched between a wall and the other car, where it may slow down, but sometimes it does hit the wall.
But you're basically taking the approach where you're going to say, I see the other car's pose, I've got its velocity, I'm going to expand the occupied area a little bit, and that's how I'm going to deal with moving obstacles. You're just treating them like a larger static obstacle. Is that correct?
Yep. Yep.
Do you compute time to collision between your vehicle and the other vehicle?
We do. In general, any obstacle from the laser scan.
But so the obstacles that are moving need to be treated differently. I guess you're computing time to collision to the blown up obstacle, the bigger one? Or are you dealing with their velocity vector?
That was in potential fields. So we do not consider time to collision with the blown up obstacle. It's just with the obstacle itself, because we use the laser scan data and that. Yeah.
But are you treating it as static or as moving?
It's as static at a particular time instant.
So technically, the formula for when it's moving should be different. But I have to think about it if static would be conservative or not. I think it would be. Okay, thank you. I think that's most people's questions, including mine.
Yeah, good questions. So let's move on to team 2, and so you guys can introduce yourselves, and then again let's ask a lot of questions. Everyone's methods are different.
Cool. I guess I'll start off. So we're team 2. I'm Chayton. My 2 teammates are Brandon and David. I guess to start, we can give a quick overview of the things that we'll probably talk about. So we're planning on first just doing a quick tangent to cover one of the alternative methods that we tried out that we thought could be interesting and fast, that we called narrow gap follow. And then after that, we'll talk about the components of the solution that we ended up submitting. And so that ended up being a combination of MPC, RRT star, and some opponent predictions. So I guess we can start by talking about the narrow gap follow method that we tried out. And so basically the inspiration for this for us was that we noticed that, especially in the first simulator, follow the gap worked really well at finding good paths in cluttered environments, as well as just moving quickly when the environment is not cluttered. So our idea was to simulate more of a closed map environment by essentially making a second map file and loading that in and simulating the scans as if they were from that map file based on our location in the odometry. And so what that ended up being was the map obstacles ended up being increased in size, and then we dynamically look for new obstacles as well as the opponents. And then once we have this simulated scan, we just ran follow the gap with that simulated scan to create this sort of narrow gap follow algorithm. So when we did this, we found that it actually was not. So we ended up doing this relatively late. This was just a idea that we had that we wanted to try out, and we didn't find it to be particularly fast, so we didn't spend a lot of time on it. But we think that if we had a long time to tune the parameters, it could potentially be really strong. And I think I saw a question. How did you define and generate the closed map? So we sort of manually made the map. So we took the image file from the original map, and we just sort of drew over it to make a smaller map.
Yeah, literally, I pulled up Microsoft 3D Paint on my Surface, and I drew a good like center line around it, and then I just took a thicker brush and drew that around the center line, and that's pretty much how I defined that.
And if you look at the GIFs on the right, you can kind of see those simulated scans creating those boundaries for it to follow. And when we were doing this, we tried to check some different trade-offs that you can get from this method. One of the big hyperparameters that we wanted to check was sort of how wide of a path you gave. And basically sort of the wider it becomes, the less optimal your paths are going to be. So you're going to be going slower. But if you have a really narrow path, then if there's an obstacle obstructing a good amount of that path, then you're obviously going to fail, right? So you end up being a little bit less robust.
So that is one of the weaknesses. Is if the obstacles is blocking the entire path, then it fails. which is why we didn't really, we talked about implementing this, but we didn't really actually implement it until we found out that the final race had no static obstacles, because we always knew that was a concern. And that's the other thing, is like the wider that path is, the slower the car is. That's like the trade-off there, but it becomes more robust that way. Sorry, I just had a question.
Yeah, and we didn't see, I mean, we didn't actually test how robust it is if it moves out of the path, because we just didn't test it, honestly.
What happens if it goes out of the path is that it doesn't get any more driving commands, and so it just kind of coasts. So if you can get lucky and get back into the path, but if it doesn't go back in the path, you crash.
Yeah. But yeah, we didn't spend a lot of time really refining it and making it robust. It was more just an interesting thing to try out, just because we thought potentially it could be fast and work well in an environment that's like not super cluttered.
Our best lap time with this was about 15.5 seconds. So that's when we saw that, we were like, okay, let's not spend too much time on it.
Yeah.
Next section we talk about is our MPC. This is majority of our time was spent developing a model predictive controller, as well as merging that with our RRT star algorithm. So I'll kind of talk about how we formulated the model predictive controller and some of the kinks that we had to work out. So first, to get the dynamics, we looked at the paper that was suggested to us that the simulator follows, and we follow the simulator dynamics almost to a T, besides linearizing it. As you see, so when the simulator, when it goes at slower speeds, it uses the kinematic model, which you see to your left, and then when it's higher speeds, most of the time it's using the single track model, which implements the slip angle and the angular velocity. And then the reason why we used acceleration as an input is because linearizing around the angular velocity, the FZR term and the FZF term has an acceleration part in it. So if we were to do like a velocity desired, linearizing that became very painful. So we just left it in acceleration. And so linearizing, this is where actually in formulating the model predictive controller, a lot of our time came down to linearizing and some little tricks in here. So one of the first things we noticed, and you can see this especially when you linearize some simple things like cosine theta, is that you get this affine constraint where it's only linear terms that you need to add into it. So we didn't fully linearize the single track model because those equations become really big. So instead of, we just did it term by term in the Jacobian with the continuous, and then did a zero order hold to discretize it. So that's why we just computed the continuous dynamics and then just subtracted them from the linear dynamics, and you get this affine constraint. And if you notice, that's what the difference between the ones on the left and the right. The results speak to themselves. This bottom graph is the open loop trajectories as the MPC is progressing, and it starts at 0, 0, and we feed it a waypoint of, it was like 2, 2, and we just have that waypoint continuously move out so it doesn't catch up, because when it catches up to the waypoint, then it passes it, then it comes back. So if you notice, without the affine constraint, the orientation of the car is almost perpendicular to what it should be. And when you add it in, that's when the arrows start to line up. And that helped quite a bit. But we were still kind of noticing that the path was a little ski-wompy here. And when we did some other waypoints, like made it go directly down a line, we noticed that it wasn't giving us optimal trajectory. So we knew something was still a little off with it. So then we decided one of the biggest performance differences is that we linearized it around the previous solution. That way the linearization point is closer to where the car actually is. And as you can see, you get the open loop trajectory follows the waypoint pretty closely, and the resulting path that you get is pretty close to where you would expect it to be.
Yeah, and I guess for us, sorry.
Oh, go for it.
I was going to say, one of the things that we struggled with for a while in figuring out, and these sort of bottom plots helped us look at, was when we were looking at our earlier plots. So the ones on the left, you can kind of notice that the RRT planned paths are not tangent with the curve to start off. And that was part of what was causing our model to jerk and oscillate. And so one of the really good advantages that we found when we were linearizing around a previous solution is that our MPC paths are really good at starting tangent to our current trajectory. And that really helped tracking in the simulator a lot.
And yeah, as you can see, the plots are in MATLAB. We coded up the simulator dynamics in MATLAB to be able to debug and visualize the MPC first to help us out with debugging, which I think helped quite a bit too. So here's our the optimization problem. It's pretty much the ones from the OSQP Eigen website. They kind of give you an example one of how to turn this optimization problem into a QP. Really, the main difference is that we added this C is our affine constraint that we added. Other than that, it just tracks the difference between the given reference and its current state. So this would be the previous X star given, and the reference point was what RRT gives it. And the results, and then the waypoint formulation, we kind of did something similar to team one where we gave the narrow map and just let follow the gap at full speed. This map kind of cuts, if you notice, it cuts into the corners a little bit. That's because when we were drawing this, we knew that the follow the gap was following the outside line. So we kind of cut it a little close so that way the outside line is still, as you can see, within the actual obstacle. And with this, we could get a lap time about 11.3 seconds. And we knew from milestone 2 that there was about 10.9 was probably as fast as we were going to get. So without doing an optimization, doing the CMAS, we figured 11.3 is probably about pretty good enough. And so here's the results with the MPC tracking that waypoint path. The red line is the full X star solution. And you see it goes past the waypoint because we tell it to hit that waypoint at 4.5 meters per second. So it goes past it and it tracks it. You can see it tracks it pretty well. So.
Yeah, so beyond just the MPC controller, we used RRT star for our dynamic obstacle avoidance. So this is just a quick video of what we submitted for our motion planning lab, and that's kind of what we built off of. Next slide, please. So one thing we tried is pruning our RRT trees. Basically, what we do is when we find the optimal path that we want to take, we walk backwards along the path and check if there's any collisions between our root node or whatever current node that we've already chosen and future nodes in that tree. This gives us straighter, more consistent solutions, and it allows us to sample a bit less and get very similar paths between tree generations with fewer sampling. One thing we figured out a little bit too late is we probably should have gone an extra step and turned these into splines. That probably would have helped our performance later on, but you'll be able to see that a little bit later. Next slide, please. So we started thinking about how we want to combine RRT star with dynamic obstacle avoidance. And so the first thing we need is a prediction for the opponent car. We basically more or less just followed the outline in the Vision Lab, where we plan a pure pursuit trajectory and combine that with their linear current velocity. We attempted to build the opponent an RRT tree to get a little bit of a more accurate prediction. However, that ended up being too computationally expensive. Yeah, next slide, please. So the way we went about combining dynamic obstacle avoidance in our RRT tree, excuse me, in the part where we check the edges of the tree for collisions, we actually run a scan against the opponent's trajectory. We come up with a time estimate for our RRT path by dividing the cost between nodes by a nominal velocity. We just use the maximum velocity as it's a little bit conservative. And so what ends up happening is we can actually get RRT star paths through their current position because we're predicting that they will be out of the way by the time that we get there. And this was a little bit hard to illustrate in the simulator, but you can see here the RRT tree stops growing kind of in front of both cars. This is where the predicted time that we would be at those locations. We essentially were guessing that we were within a certain threshold of the opponent's trajectory. So the RRT detects a collision there. We did this by finding the time segment along each RRT edge and the time segment along the each segment of the opponent's trajectory. You can then do just a simple quadratic minimization, just analytically, to find the time at which those lines are closest, or at least points along those lines are closest, and compare that to some distance threshold. Next slide, please. So in order to combine both MPC and RRT star, we essentially fed in our first segment of our RRT tree into the MPC controller. And that's basically how we transferred it over. We were initially planning on using half-plane constraints around our RRT edges to make sure that the MPC controller didn't violate any detected obstacles. So we did implement that, but we found that it didn't make very much difference, and it increased the likelihood for infeasible solutions to be found by the MPC controller, which would, wreak havoc. Yeah, so next slide. Jayden, do you want to explain this part? No? Okay. So another thing that we did...
sorry, I was muted there, David, my bad.
Oh, go ahead.
yeah. I was answering some of the questions in the chat and didn't realize. So another thing that we found worked really well for us was sort of making all of our components function asynchronously. And so this prevented us from getting bottlenecked in any part of our planning and control process. And also it let us publish faster, which ran the simulator faster, which helped for iterating, especially when we started trying to overtake opponents and you kind of need to run the simulator for some time. It helped us iterate faster. And so the way we ended up implementing that was we separated our MPC from our RRT star and our publishing from our MPC. And the way that we did this was we had RRT star create a path and save it as a member variable. And then we would have our RRT star node be a member variable within our MPC node so that it could access that path and plan with the most up-to-date path. And this worked particularly well because our publishing could be faster than our MPC, and our MPC could be faster than our RRT star. So this let us try to stay as up-to-date as possible. This is another place that if we had more time, we would have probably done it differently. We ran into some problems in development that because all of our code was sort of nested within one another, it made it difficult to be modular and find errors when we made changes. And so if we were to do this again, we would probably use nodelets and shared memory to try to make development a little bit better and the code a little bit more readable. Can we go to the next slide? I think, and so next we also want to talk a little bit about our race strategy. And so this is particularly something that we were thinking a lot about after we found out that there's not going to be static obstacles for the race. And so one thing that we noticed is that if you're already in front of the opponent car, or if you're kind of far behind them, you can basically just track your pure pursuit trajectory, and that'll work really well. Especially because we found that that was sort of our, or sorry, by pure pursuit trajectory, I mean sort of a preset list of waypoints that we had bankers think is close to an optimal path. And we only really need the extra machinery of the RRT star when we're trying to go for an overtake against our opponent. So our strategy is to primarily just track the waypoints directly with MPC. And once we're close to the opponent, or the opponent is close to the points that we're tracking, then we switch to RRT star to try to overtake the opponent. One trick that we found worked really well for this was we used a different set of waypoints for RRT star than we did for our normal tracking. And we set the RRT star waypoints to be sort of wider around the track. And this encouraged our car to sort of overtake from the outside edge, because we found that whenever the car tried to overtake on the inside edge, this led to a lot of collisions as you get cut off really often as you're trying to round the corners. And so by setting the RRT star waypoints a little bit wider, we overtook from the outside edge, and that definitely helped us out a lot. And then sort of a final policy for our racetrack strategy was we set sort of a threshold speed that if the opponent is going above that speed, then we just don't even bother trying to overtake them. We just try to stay near to them and slightly behind by slowing down whenever we get too close. And this is because we found that once the opponent gets fast enough, especially because we're taking the outside edge, we're unable to actually get around the car in a reasonable amount of time. And so it ends up causing more trouble than is worthwhile. And so when the cars are going similar speed, we just try to track from behind and sort of cede the ability to overtake. Oh, you can go.
Okay. So as we mentioned before, if we were to do this again or had more time, one thing we would definitely look into is using splines instead of straight line pruning for RRT star. We think this might actually help our MPC solutions if we were to linearize around a spline instead of just the previous solution. Another struggle that we had was when our car gets too close to the other car, RRT star has trouble making trees because it detects that a collision is inevitable when maybe it isn't. And that just comes down to the heuristic distance we want to keep from other cars. So that is something that we just tried to tune out, but looking at a better, more general solution would definitely be something we would want to do. And of course, just continuing to improve our optimized race line.
Yep, that's our project.
Yep. I think you're muted, Professor.
Yeah. Okay. Good job, guys. So I think there are a couple of questions you can answer that are posted here besides the implementation ones, just on the overtaking.
Do you just want us to answer in the chat and then we can?
No, you can just answer. You can just mention the question verbally and answer it verbally.
I guess one that we didn't actually get to answer in the chat was about the time horizon and the MPC. And one thing that we noticed is that the MPC was quite sensitive to the time horizon, but we weren't really able to nail down how to really optimize it. We just sort of empirically found a value that worked well and stuck with it. But I don't think we necessarily have great intuition about why it works well, per se.
Yeah, our time horizon is 20, is what we put it at. It
it's
seems
like 20
to work pretty
time
well.
steps. Yeah.
Yeah, 20 time steps.
And we set our time steps for MPC to be the same time steps as our publish rate, so that as we're publishing, if MPC hasn't updated yet, we can just publish the next control from our U star generated by MPC. So it's 20 steps at 80 Hertz. Or I think actually in our final solution, we might have upped that to like 30 steps at 80 Hertz or something like that.
Did you guys do any experiments comparing tracking with Pure Pursuit versus the MPC? Was it worth it?
I don't think we directly compared them, or at least not Pure Pursuit. We did compare against RRT though, just essentially doing kind of just steer towards the first node in the RRT tree, and that definitely had some upgrades, or the MPC definitely had an advantage over that.
I guess what I mean is, like, without the half space constraints, you've written a tracker which follows a path, right? Is that wrong to say?
No, that's about right.
Yeah.
So I suspect that this was actually quite worth the effort because your tracking error from the reference path is going to be quite a bit smaller. And that enables you to make these sort of close quarters overtakes more easily than if you use Pure Pursuit. And so I was just wondering if you'd characterize sort of the average tracking error or tracking error during overtake maneuvers. Because if you're trying to get through a thin gap, right, and you're 0.1 meter off, that's toast for your car. So
right.
I think would be my motivation for
the
solution.
I think for us, it gave us some improvements definitely at high speed, because we were able to sort of handle slipping much better since we were integrating that into our dynamics. And it also gave us a more sensible way to weight different parameters of our trajectory tracking. So, like how much we're willing to have high steering angles, or how much we care about being fast versus being accurate, and things like that, because you get those natural components in the cost in your MPC formulation.
There was some questions sort of in the weeds about, should you have used nodelets? Does it even matter if you're really not shipping that much data back and forth? And yeah, do you have any thoughts on that topic?
I mean, I was just thinking that there would be some latency to the publishing and subscribing implemented by ROS. And so that's why we would have liked to use shared memory. And that's essentially what we implemented in a more messy strategy by just sort of having our RRT node be like a member variable for our MPC node.
Yeah.
So we would have liked to use nodelets to have that shared memory capability, because because especially we were doing things asynchronously, we wanted to make sure the latency from one component to another was as small as possible.
Yep. Yeah, I think it was probably the right answer for the future, to use nodelets here. Even though it's not a lot of data going on across the bus, it's extremely important that it happens quickly. I think one other thing, I know you guys didn't have a lot of time with the real car, but the rate that you're able to get scan messages at and position updates, do you think that made a difference? Like, so you wouldn't really be able to run at 80 hertz without some fancy footwork on the real car. You're only getting laser scans at 30 hertz normally.
So I think our MPC was running at like 30 hertz and our RRT similar, but our publishing was much faster.
I see. So you're sort of running open loop in between the updates.
Yeah, because when you compute the MPC, you get a U star based on your discretization of your time steps. So you maybe get like the next sequence of 10 controls you should take. And so while we're waiting for the next MPC or RRT update, we just go along that sequence of controls and publish them one by one, rather than just taking that initial control and publishing that alone.
Mm-hmm. Yeah, I think an interesting future project for somebody, I was thinking about this today, would be to add an IMU that's running at like 1,000 hertz and common filter it with the poses from the particle filter so that we can get faster pose updates. I think the frequency which you publish drive messages seems to matter a lot on these cars in the two-player racing scenario. I think it's really good presentation, and I'm impressed with the project. Thank you.
Thanks.
Thanks.
Good job, guys. So we'll switch to team 3, but I'm going to pause this recording now. Otherwise, the file will become too large. And yeah, so team 3 can start sharing.